Alright, today we're going to talk about evaluating functions. Now, before you get all panicked, it's not much new, but it's just a different way of doing something we already do. And it's called functional notation, and we're going to work with expressions like algebraic expression x plus 2. And again, it's an algebraic expression because it has a variable x in it. Two terms, this is a two-term expression. And we've been evaluating expressions. We've been saying things like, if I have the expression x plus 2 and x is 0, what's the value? Well, we put in 0 and we get 2. Or we could say we have the same expression, x plus 2, x is 5, and we get 7. And the question becomes, if I tell you 2 or 7, you know, sometimes we can evaluate it at multiple points. So how do we know what x value is used? Well, as x changes, the value changes. So often we write an equation for those types of situations. We say y equals the expression x plus 2 and make an equation because of the equal sign out of that expression. So if x is 0, y is 2. If x is 5, y is 7. Again, we plug in those values back in the original equation. So if y is 3, what's x? Well, that's not that hard. I'll grab my marker here. You probably can do it in your head, but you say, oh, wait a minute. I have y equals x plus 2. Well, if I put 3 here and I say x plus 2, this is one of those situations where you can just look and say, yeah, x is 1. Not that hard. But we can make it a little more difficult. You have the expression, or the equation, y equals x plus 2. Well, what if y is 1/3? Well, that's a little more work. 1/3 has to go here. You have to take away 2. It's fractions. Now, trust me, it's negative 1 2/3. All right. 2 minus 1 2/3 is 1/3, or negative 1 2/3 plus 2 is 1/3. It'd be easier to track x and y as a pair, though. So, thus, we have what we call function notation. Instead of y, we have this f of x equals the same expression. And it's not f times x. This is not two variables. This is replacing y. And we can say, hey, when f has negative 1 2/3 for x, the expression is 1/3. So you can see up here, that whole notation takes care of x and y. And up here in the upper left, I took a second and I plugged in negative 1 2/3, showing how it just substitutes into the expression side and replaces the x value. So f of negative 1 2/3 is 1/3. It is the same, this is congruent, this is the same as evaluate the expression x plus 2 at x equals negative 1 2/3, which again would result in 1/3. So when x equals negative 1 2/3, the expression of f of x, which is x plus 2 in this case, resulted in y is 1/3. It is a shortcut notation. It's important, though, that we realize it's a notation that we want to track. So, if I put two examples on the board, we'll start with f of x, then we'll do g of x. When you see a letter f, g, or h with parentheses x, that is not f times x. It is a function of f of x. It's one thing. So here it says f of negative 1. So I had x squared minus 3, so I have x squared minus 3. And this time the x value is negative 1. Negative 1 times negative 1 is 1. 1 minus 3 is negative 2. But we don't just write that, we write what value it was. F of negative 1 equals negative 2. For 3, we just go 3 squared minus 3. 3 times 3 is 9. 9 minus 3, f of 3 is 6. For the last one, f of negative 4. Alright, negative 4 quantity squared minus 3. You notice I don't write this, because it's not equivalent. I have to replace the variable with parentheses. I get 16 minus 3, I get 13. I get f negative 4 equals 13. Sticking with our radical discussion with exponents and whatnot, I don't have to have it be clean. Square root of 2, quantity squared minus 3. Remember, that means square root of 2 times square root of 2. That's my cat saying he approves of what I'm doing. 2 minus 3, and I get f of square root of 2 equals negative 1. And again, every time I do this, I have a function notation. Over here, Same thing, g of 2. Okay, replace all the x's with 2. 1 over 2 plus 3 minus 2 plus 1. That's 1/5 minus 2 plus 1 minus 2 plus 1, so I get 1/5 minus 1, negative 4/5. And again, that's g of 2. All the calculations over here resulted in negative 4/5. How about g of negative 1? Okay, well, 1 over negative 1 plus 3 minus a minus 1 plus 1. I get 2 here, 1 plus 1. I get 1/2 plus 2. I get g of negative 1 equals 2.5. The last one I put up was g of negative 3. And again, when you fill it in, hopefully you catch right away the problem here. I get 3 plus 1 is 4 over here because it'll be double negative, but you got to catch what happens in the denominator. 1 over 0. So g of negative 3 is not possible. It is undefined. Again, function notation. You notice every time I have the value that it results in, I have the x value shown. Last slide today, I have some examples here. If you pause it, I'm simply going to write up the answers as fast as I can. I'm going to start with f of x, then I'm going to go to g of x, then I'm going to go h of x. And again, this is good practice, all right? Make sure you do parentheses. On this one, be careful. Negative 2 squared is positive 4. And the negative outside, there's 3 negatives there. That makes this negative 4. Likewise, on the negative 10, it doesn't have to be pretty. It can be big, too. Finally, on the last ones, make sure that you realize that this here is the same as this for the bottom two fractions. It's 1 over 1 over x when you plug in the fraction ones. So again, I plug in two negatives on that one, make a positive. And finally on the last one, I'm just going to use the 1, 1 because I'm running out of space. 1 over 2/3 multiplied by the reciprocal. Watching our signs. And again, practice these function notations. Realize that this is not h times 3. This is simply h of 3. When you put x is 3 into the function or the expression of this, you end up with the y result. It takes some practice.